again, welcome to AP Calculus 3.9a Homework Solutions. We're going to do on page 226 numbers 3 through 13 odd. I went ahead and put the solution to number 3 up here. So we've got this table. Our equation's x to the fifth. So to fill out the top, I just took 1.9x and raise that to the fifth power, so that's 24.768, and we did that to 1.99 to 2.01, 2.1, and we got f of x for these 5 x values. Then to get our tangent line equation, which we want to compare to our f of x, we would take the derivative of x to the fifth, which is 5x to the fourth, and then you get the tangent slope by plugging in 2 for x, because our x value here is 2. So 5 times 2 to the fourth, that's 5 times 16 is 80, so that's our slope. So our tangent line equation is y minus 32 is equal to 80 times x minus 2. So if I take that 32 and put it over to the right side, make it positive, and then distribute 80 across x minus 2, I would have y is equal to 80x minus 128. And so then I have to plug in those 5 values into that equation. So 1.9, 1.992, 2.01, and 2.1. And you can see the values that I got here. So 24, 31.2, 32, 32.8, and 40. And you can see that near the point of tangency, which is 2, so if we go to 1/100th to the right, you see that we're only, 8 1/100ths away from the initial 32.8. So, there you go. But, or 8 1,000ths, excuse me. And the same thing here, we're really close, 31.2 versus 31.208. But as you get a little further away, you get a tenth away, now we have a difference of 0.8, so our error increases as we get further away from 2. So that is the point of these problems, that the tangent line emulates the curve close to the point of tangency. All right, and let's go ahead and do number 5. So again, we have f of x, and then t of x. So it's the same numbers. All right, 1.9. Give myself a little more space this time. 1.99, 2.0. 2.01 and 2.1. Okay, our f of x is sine x, and we are at the point 2 and sine 2. All right, I'm going to go ahead. So sine 2, that's already in my calculator, did a minute ago, is 0.909. Now, your calculator has to be in radians. So I'm just going to go ahead and put that as a decimal out to 3 decimal places. But that's all sine 2 is. So let's go ahead and plug these numbers in, all right? So if you plug in sine of 1.9 into your calculator's in radians, you get 0.946. And 1.99, you get 0.913. 0.909, which of course makes sense. 0.905. And then 0.863. Okay, so we've got that top part filled out. We need to get the equation of the tangent line. So the derivative of sine is cosine. So our tangent slope is going to be the cosine of 2. Okay, so plugging in the cosine of 2, you'd have negative 0.416. So our tangent line equation, y minus y1, 0.909, is equal to the slope, negative 0.416 times x minus 2. Now if I go ahead and shove that negative 0.909 over to the right, distribute the negative 0.416, we would have, and instead of y, I'm going to put t of x, is going to be negative 0.416x plus 1.741. Okay, that's negative times a negative makes a positive, and then you have a positive 0.909. That adds up to 1.741. So we could do t of 1.9. That's negative 0.416 times 1.9 plus 1.741. And that is equal to 0.951. And then you would do that for all the rest. 1.99, t of 2, which of course is going to, t of 2 is going to be 0.909 because those are equal. T of 2.01 and then t of 2.1. Okay, and I'll just fill these numbers in. You would just put that right in your calculator. You could even type over, the 1.9, put 1.99. But if you don't make a mistake, you're going to get 0.913, so that's right on. So this tangent line does emulate the curve very well. If you're only 1/100th away, you can go out all the way to the thousandths place, and the same thing through right here, 905. And then for 2.1, you get some divergence. It is 0.867. All right, so when I've had students make mistakes on that, it's just because they didn't use radians, although I do think I put in your lecture, I told you in your lecture to make sure your calculator is in radians. Okay, the rest of them are going to be a little shorter. Those two were a little more tedious. So number 7, we want to use the information to evaluate and compare delta y to dy. So we have y is equal to x cubed. We have x is equal to 1. And delta x, which is dx, is equal to 0.1. All right, so delta y is equal to f of x plus delta x minus f of x. That's going to be f of 1.1, right? 1 plus 0.1 minus f of 1. So f of 1.1, that's going to be 1.1 cubed minus 1 cubed. So delta y is 0.331. Okay, so let's compare that to our differential. So our differential dy dx is equal to 3x squared. Right? The derivative of that, 3x squared. So dy is equal to 3x squared dx. So that's going to be 3 times 1 squared times 0.1 dx. All right, so that is 0.3. Okay, so in this case, you know, our estimate is okay. We have an estimate of 0.3, an estimate of 0.331. But you are, 0.1 is 10% of 1, so you're really not super close. So that's why the estimate is kind of meh. But that's what it is. All right, let's see if we can get one that's maybe a little closer. Number 9. We have y is equal to x to the fourth plus 1. X is equal to -1. And delta x, which is dx, is equal to 0.01. All right, so this time you're only, instead of 10% difference between x and delta x, it's just a 1% difference. So I'm expecting to be a little closer here. All right, delta y is equal to, again, f of x plus delta x minus f of x. That's going to be f of, all right, x plus delta x, -1 plus 0.01. That would be -0.99 minus f of -1. All right, so that would be -0.99 to the fourth, right, and plugging it in, plus 1 minus -1 to the fourth. So let me put brackets around that. -1 to the fourth plus 1. So -0.99 to the fourth plus 1. All right, that is 1.961. And then that'd be 1. -1 to the fourth would be positive. 1 plus 1 is 2, so -2. So delta y is -0.039. It's actually more work to get delta y. And then we would have dy dx, we're going to take the derivative, is equal to 4x cubed. So dy is equal to 4x cubed dx. So that's going to be 4. X is -1. Got to cube it. And times 0.01. So that's going to be -1 cubed is -1 times 4 would be -4 times 0.01 would be -0.04. So that is dy. So those two, they're within a 1/1000th. So I would say that that is pretty good. Now you're not going to have to, on the test, give me your opinion on how good it is, okay? You'll just have to plug the numbers in, all right? But anyway, the reason the estimate is better is because dx is smaller. It's closer to the curve. All right, and then 11 and 13 are going to go real fast. Okay, number 11 just says find the differential dy. So we have y is equal to 3x squared minus 4. So dy dx is equal to 6x. So dy, multiply both sides by dx, is 6x dx. There you go. And then 13, y is equal to x plus 1 over 2x minus 1. So the derivative of that dy dx would be the bottom, 2x minus 1, times the derivative of the top, which is 1, minus the top, x plus 1, times the derivative of the bottom, which is 2, all over 2x minus 1, all squared. So that's 2x, negative 2x. Those are going to cancel. And then you'd have negative 1 minus 2. So that's negative 3 over 2x minus 1 all squared. So multiplying both sides by dx, we'd have negative 3 over 2x minus 1 all squared dx. All right, that'll do it for this solutions video, and I will talk to you on the next lecture.